Precal lesson. Alright, so in this section, Unit 8-3, the topic here is unit vectors. And so when we're talking about a unit vector, alright, so really the unit vector, and it has the same direction as a non-zero vector v. And so in order to find the unit vector, really all you got to do is take the vector and divide it by its length or by its magnitude. So the unit vector is going to be equal to whatever the vector is divided by the magnitude, right? And so that would be a unit vector, so a vector that has a magnitude of 1 in the same direction of the original vector that you had, which is v. All right? And so use a scalar multiple of v. Let's see. The unit vector has a magnitude of 1 and it has the same direction, and then that's your unit vector. And so first thing that we come to is the type of problem where it asks us to find a unit vector in the direction of a given vector and then verify that the result has a magnitude of 1. So the vector that we're given right here, this is the component form, so -2, 5. So to the left 2, down 5, that would be the vector, the terminal point, and the initial point. So to the left 2, down by 5 to get to the terminal point. And so we want to find the unit vector in this same direction. So a vector that's going the same direction but only has a magnitude of 1. So how do we do it? We want to take the vector and divide it by its magnitude. Take the vector and divide it by its magnitude. So how would that look? That would look like this: -2, 5, the component form. And we would want to divide that by its magnitude, which would be the square root of -2 squared plus 5 squared. And remember, the operations that we looked at last time says a vector can be multiplied by a scalar or divided by a number. And so when that happens, it'll look like this. Still on top, we got the component form. So that would be -2, 5. Simplifying on the bottom, we can get this. That would be 4 plus 25. And still the component form on top. And all that's over the square root of 29. Okay, so from here we've got a component form of -2 over the square root of 29, comma 5 over the square root of 29. And then that is my component form. We need to clean this up just a little bit because we don't want the root into the denominator. So what I'll do is I'll multiply the top and the bottom times the square root of 29, and we'll come up with this: -2 square roots of 29 over 29 and 5 square roots of 29 over 29. And then that is going to be your unit vector. Okay. It also says verify that the result has a magnitude of 1. In order to do that, you can just take it and put it into your Desmos calculator and see that if you were to take the magnitude of this thing, that it is in fact equal to 1. So what have we found? We found the unit vector to this vector. It's in the same direction and its magnitude is equal to 1. Okay, so that's the procedure for finding the unit vector. Let's find another one. Let's say we want to find a unit vector with the same direction as this one. Okay, so same idea. The unit vector is found by taking the vector and dividing it by its magnitude. Alright, so here we'll have -2, 3. We'll want to divide that now by the magnitude, which is the square root of -2 squared plus 3 squared. And so that would be equal to negative 2, 3. And all of this now will be over, that would be 4 plus 9, so that would be the square root of 13. Alright, so from there, we can go negative 2 over the square root of 13, comma, 3 over the square root of 13. And once again, we need to rationalize the denominator, get the square root out of there by multiplying the top and the bottom of each one of these by the square root of 13. When we do, we ultimately end up with this. Negative 2 square roots of 13 over 13. And 3 square roots of 13 over 13. And then that is the unit vector. All right. Okay, so the next idea that we come to is we're talking about the standard unit vectors. All right, so these two vectors, 1, 0 and 0, 1. So the unit vector that is going to the right and has a length of 1, right? And the one that is going straight up by 1. Alright, those are called the unit vectors, standard unit vectors. Okay, and they're denoted by these two component forms. And I stands for the horizontal standard unit vector, and J stands for the vertical standard unit vector. Alright, and notice that it's a lowercase boldface I to distinguish it from the imaginary number I. Alright. And so these vectors can be used to represent any vector, okay, by taking the component form, all right, and multiplying each one of the components times the unit vector, which can then be replaced with the I or the J, and then take the sum, right? So this component form, you take each component, multiply it by the unit vector, and then combine those components together. So the horizontal component is multiplied by the horizontal unit vector. The vertical component is multiplied by the vertical unit vector. Then this is changed from its component form to its representative I and J, respectively. And then this is a form, okay, where you can take the component form of the original vector, multiply it by the standard unit vectors, and take the sum. Now these scalars are called the horizontal and vertical components of V, so we know that. So this vector sum then with the horizontal component times the horizontal unit vector plus the vertical component times the vertical unit vector is called a linear combination of the vectors of I and J. So any vector in the plane can be written as a linear combination of the standard unit vectors I and J. So what do we mean by this? So let me just take any vector. Let me take this one for example. Let's say I take the unit vector whose component form is 5, 12. All right? So that means over 5 up 12, that's the terminal point. Okay? I can take that and write it as a linear combination, right, of the standard unit vectors just by taking the horizontal component times the horizontal standard unit vector I and adding it to the vertical component times the standard unit vector J, and then this component form is now taken and transferred to this linear combination form. And so the reason why this works is now we're taking 5 and multiplying it times that standard unit vector of 1, so it's a vector that comes this way. So in other words, if I have my original vector that was over 5 and up 12, right? Over 5 up 12, there was my original vector. If I write it in this form, I'm just taking the standard unit vector, multiplying it and giving it a length of 5, right? I'm taking the vertical component, multiplying it times 12, Well, if I take those two and add them together, put them end to end, then the resultant vector is the same vector that I have. That's 5 and 12. All right? So this is just another way to write this. And the reason why we're doing this here now is it's going to become more convenient to write it this way in the subsequent sections coming up, and you'll see what I mean when we get there. Okay, so what type of problems are we practicing from this? Okay, so we want to find the vector with the given magnitude, okay, and the same direction as u. Okay, so I want to find a vector that has a magnitude of 8, but that is going in the same direction as 5, 6. Now, 5, 6 doesn't have a magnitude of 8. So I need to find the vector that is going this direction, but does have a magnitude of 8. Because if you were to do the square root of 5 squared plus 6 squared, okay, you would see that the magnitude here is not going to be 8. But we can turn it into 8, okay, by following this procedure. So the first thing, let's talk it out. The first thing we'll do is we'll take u and turn it into its unit vector. Once we turn it into its unit vector, okay, then we can multiply it times 8. So we'll turn it into its unit vector, then multiply it times 8. So again, the first thing I want to do is take this and turn it into its unit vector by dividing it by its magnitude. All right, so I'll have 5, 6. Okay, we'll divide the thing by its magnitude, which is the square root of 5 squared plus 6 squared. So we're still at 5, 6. And we're dividing by square root of 25 plus 36. So again, 5, 6. And that's going to be the square root of 61. All right. So now we can take this and write it as a component form of 5 over square root of 61, comma, 6 over the square root of 61. And so rationalizing it now, we will have 5 square roots of 61 over 61, comma, 6 square roots of 61 over 61, and that's my unit vector. Okay, now I took it down to the unit vector because what I want to do now is I can, once I have it down to 1, I can multiply it by the correct scalar. So now that it's down to the unit vector, I can take it and multiply it times 8, okay, which would then now give me this. So we'll go 8 times 5 and make that 40. So that's 40 square roots of 61 over 61. And 8 times 6, 48. So 48 square roots of 61 over 61. And ultimately, now I can take this and write it in the new form that we've just learned about, the linear combination form, and finally get this now as a final answer. That would be 40 square roots of 61 over 61i plus 48 square roots of 61 over 61j. All right. So this is the answer in component form. This is the answer in linear combination form. All right. So we have another problem very similar to that. It looks like this. I want to find now a vector with a magnitude of 10, okay, and that's given in this direction. So 2i minus 3j. So now instead of being given in component form, they're giving us this in linear combination form. So we have to be comfortable with using both of the forms. All right, so how do we do it? it'll be u over the magnitude of u, which is now going to be 2I minus 3j over the square root of 2 squared plus negative 3 squared, which is going to be 2I plus 3j over square root of, that would be 4 plus 9. So we've got 2I plus 3j. Oh, change that minus to a plus somehow by accident. Didn't want to do that. Let me change it back. It's still a minus. But that is over the square root now of 13. And so when I divide this out, I can now get this. Two square roots of 13i over 13 minus 3 square roots of 13j over 13. And this is now the linear combination form, okay, of the unit vector. That's the linear combination form of the unit vector. But I need to now multiply this times 10, because I need one with not a magnitude of 1 in the same direction, but a magnitude of 10 in the same direction. All right. So when I multiply that out by 10, here's what we get. 20 square root of 13 over 13. We'll keep it as an I minus be 30 square root of 13 over 13, and then that'll be my j, and then that's the final form of the answer that we want. All right. Also, you can check to here to see if anything cancels out. It doesn't in either case. If it did, you could reduce the fraction down. But this now is a vector, okay, whose magnitude is 8 in the same direction as 5, 6. All right, so there you go.